Hello again. This is part 3 of linear programming, and I think I should do part 4 as well. I'll explain why in a minute. The reason I have one extra part to do is because I've just noticed something that on our slide, this is where we stopped, by the way. So we stopped here, and the next slide was sensitivity analysis. Our slide it starts with sensitivity analysis, whereas uh, in the PDF file, I saw something which is worth explaining. So this is what I want to explain in part 3. Now, this is where we stopped, and I don't want to go through this. This you can listen to the tutorial on in part 2 of linear programming. But um, what we have further down would be another method to find the binding constraints and the non-binding constraints and the small x and small y and the profit and so on. So I want to focus on this as well. So what is what I did here was brief summary of method 1. So there you go. You can pause the video and read through. But method 1 was quite easy, and in terms of finding the solution, and we obtained our profit equation. We looked at our constraints, we plotted the lines, we understood the inequality, we shaded. If we are doing it with pen and paper and graph paper, it's advisable to shade the unwanted region so that you get a nice clean feasible region. Then we look at the points of intersections, the solutions out of millions of coordinates that I have in my feasible region. The intersection is where my maximum profit would lie. So I look at the points of intersection, and a little bit of knowledge on simultaneous equation, how to solve them, would come handy. And once I solve them, I have small x and small y, which I can substitute in the profit equation and hence get the optimum profit. That was method 1. That was part 2 of our linear programming tutorial. Now, I'm going to discuss another method here, which is method 2, and it's found here. All right. So that's just another method, and you will notice that at no point would we need a graph paper here. So we are dealing with a method where all we need is just the knowledge of of binding gradient. We don't need to plot anything, and we should get the answer. Right. So I do hope that what you see on the screen is familiar to you, and let's try to solve this with our graph. And to do that, we need to understand how to find the gradients of the profit line, gradient of the finishing constraint, assembly, and the spring constraint. So I've just done one for you, but please try to find the gradient or the slope of these 3 constraints as well, and see if you get these values here. So what I did was uh, I've considered the profit line, right? So there you go. So first of all, that's my profit equation. I've moved 30x from the right to the left, hence minus 30x. I've decided to rewrite because I like my y to be on the left, and then I've divided throughout by 100, and this is what I get. And the gradient is the coefficient of x, hence that's my gradient. So the gradient for the profit line is minus 0.3 here. Now you should try to do to find the gradient of the finishing line, the assembly, and the spring. Sorry, let me say it again: the finishing constraint, the assembly constraint, the spring constraint, and see if you get these values here. And basically, that's where I've just used Excel to rewrite them. Don't worry about this for the time being. So that's what you're supposed to get, right? So I've done this one. You please practice and see if you can get the gradients of these 3 and get these values as well. Now what we're going to do is very easy. I'm going to try to locate this number amongst these three values. So what I've done here is I'm rewriting these three values in ascending order. Smallest, the slightly bigger one, and to the largest one. Smallest, middle one, largest one. These are the gradients of the constraint. And what I'm going to do now is locate this number, which is the gradient of the profit equation, between or amongst these three numbers. And clearly minus 0.3 lies between these two here. It's bigger than minus 0.42 and it's smaller than minus 0.2. So that's where I locate my profit line gradient. And this is obtained using assembly constraint. This one was obtained using the finishing constraint. Because my gradient lies, my profit equation gradient lies between these two, that is the assembly and the finishing, then clearly these two are my binding constraint. And this one, which I didn't use at all, which comes from the spraying constraint, is my non-binding constraint. So with that graph, I know which one would be my binding constraint, this one, and sorry, there you go, this one, assembly and finishing. I know these two would be my binding constraint, and this one clearly is my non-binding constraint. Now, once I identify the assembly and the finishing being the binding constraint, the assembly and the finishing, I can solve these two equations just like method 1, solve them simultaneously to find the point of intersection, small x and small y, which would be the same answer as before, which would be this and this, and substitute in my profit equation, substitute here to get my maximum profit, and I will end up getting this maximum profit. So as you can see, at no point did we use the graph. So there you go, summary of method 2. So I've only done one gradient for you. Please practice the other three. Locate the gradient across the gradients of constraint, hence identifying the binding constraint and the non-binding constraint. Use simultaneous equation to solve for small x and small y, and then substitute in the profit equation to find optimum profit. Right, so that was method 2, which avoids using graphs. Method 3 now, I think it is, yeah, it's on page 184. Method 3 is probably slightly tedious, but nevertheless it's a method, and we might want to know how to use it. We do need the graph, and the only difference here between method 3 and method 1 is we are not using a table of values. We just need to focus on the red line. So what's the red line? The profit line, 30x plus 100y equal to p. I've drawn it in red, and what you're going to do is you're going to move this red line, so you can use a ruler to do this on your graph paper. Move the red line within the feasible region. We don't want to go beyond this. So take a ruler, place it, start from here, parallel to this red line, start from here and move up. And you will see that the red line will touch point B last. And that's where your optimal solution would lie. So it's easy in terms of method. It's tough in terms of practical, or in terms of practicality, because you need to get your ruler parallel to the red line. Hence, you can't keep moving your hands, otherwise the slope will change. So it is slightly tedious to do, but like I've said, it is a method, and it's worth knowing it. So the red line would touch point B last, and hence again use simultaneous equation to find the point, the coordinates, and substitute here in the profit equation. You'll get the maximum profit. Same solution as before. So those were the three methods to find the solution. The solution being small x, small y, and then substitute in profit equation to get the maximum profit. So there you go. That's method 3 here. Now I'll carry on a little bit more to explain One example which I noticed, and I'm not going to type anything, I'm just going to ask you to follow on the PDF, uh, on minimizing costs. Now, if you remember in part one of linear programming, we said that there are two ways of looking at a linear programming question. One is either maximizing the profit, and second is minimizing the cost. So on the slides, on the PowerPoint slides, we do not have any examples on minimizing costs, but on page 186, we do have one. So the procedure is the same. I'll let you read the the question here, and we'll figure out how to do it. And I'm only going to use, let's say, two methods, the gradient method and the graph method, to explain the answer. Well, I think all three methods are covered here. Anyway, it won't take a long time. Right, so do read the question properly and identify that it's a minimizing cost question. There you go. It is mentioned here, so that should not be a problem. Try to formulate your profit equation, sorry, your not the profit equation this time, but your cost question, which is minimizing cost. This is known as the objective function, which I mentioned in part one. So formulate your objective function, which is this. That will be your objective function, and also identify your constraints. So the answer is here. The inequalities are there, but try to come up with with those yourselves without just copying the answer, and see if it makes sense. So I want you to try these yourself. Remember, we have two default inequalities, and so on. So at least if you reach this point here, it's good news. Now, if you decide to find the feasible region, and this is what you're going to get here. We've shaded the feasible region. Now, method one would be method one would be to find the coordinates of these vertices here, A, B, C, and D. There are millions of coordinates here. They are all useless, because, as a matter of fact, the solution out of millions of coordinates will be either at A or B or C or D. It's always at the intersecting vertices here. So how do you get A, B, C, D? You can solve simultaneously. Yeah, you can solve simultaneously and come up with the coordinates which are here, and substitute in X and Y, and you will end up with the minimum cost, which to me looks like this one. So 42.5 pence at coordinate 2575, which is 25 being small x, 75 being small y, which, if I have to interpret 25 grams of food 1 and 75 grams of food 2, that was method 1, and that would be my answer here. I could use method 2, which is the gradient method. So find the gradient of the cost equation, find the gradients of the uh, constraints, and locate this one amongst the three here, and you will see that it lies between 1 and 3. It lies between -1 and -1.5. So the binding constraint will be 1 and 3. The non-binding constraint will be 2, right? So which means I will use all the resources in constraint 1. I will use all the 100 here in constraint 1. I will use all the 225 in constraint 3. I want you to try and understand what will happen for the non-binding constraint, what happens to the 250. So what you can do is substitute the x and y, substitute 25 and 75 in in 75 and 25 in here, and you will get 100, 75 and 25 here. You will get to 25, 75 and 25 here. You will not get to 50, hence the non-binding constraint being constraint 2. So that was the three methods discussed, and an example of minimizing cost discussed. Now, when we move to part 4, I will explain the sensitivity analysis. Okay, so see you in a bit for part 4.